Hi class, let's get started again. We're working on problem 17.27 from Carey 7th edition. The question is hydride reduction with lithium aluminum hydride or sodium borohydride of each of the following ketones has been reported in the chemical literature and gives a mixture of two diastereomeric alcohols in each case. Give the structures of both alcohol products for each ketone. Well, in three of the examples that we have here, A, C, and D, we have a chiral molecule. There's a chiral center here. There's a chiral centers, well, for C, there's chiral centers here, and for D, there's chiral centers here and here. And they're chiral because, in this case, because the pathway going in this direction is different from the pathway going in this direction. If we were to establish the priorities for the four carbons on this example, or for this carbon, we would have this bond to the oxygen having the highest priority, followed by, from here to here would be 2, from here to here would be 3, and hydrogen would be our lowest priority. So if we were to number these, it would be 1, 2, and 3, and we would see that the stereochemistry there, or the absolute stereochemical designation, would be 1 around to 2 to 3. So to speak, would be turning our car to the left, so the designation there would be S, but that's as far as I want to go. Now, we need to understand what a diastereomer is. A diastereomer is or a relationship, a diastereomeric relationship between two molecules is going to, those two molecules are going to have different chemical and physical properties. In most cases, we've learned this by comparing, say, a left shoe and a right shoe. A left shoe and a right shoe are enantiomers of one another. One is left and the other is right. And that is defined as having for them having mirror images of one another, but non-superimposable. And the best way that we've looked at seeing diastereomers is a relationship between molecules that have more than one chiral center, but not all chiral centers are opposite. So if a molecule were to have the stereochemistry R, R, S, S, R, 5 chiral centers, and I just made that up, by the way, the only enantiomer of this has all of the stereocenters with the opposite designation, S, S, R, R, S, for example. And if you have a molecule that has any difference or any retention in stereochemistry, but difference in any other area, they're going to be diastereomeric. So, for example, this case, these two are enantiomers, but RRSSR and RRSSS, these two are diastereomeric. These two are enantiomeric. And we could also have another diastereomeric relationship between S, S, R, R, S. You change any of these, and it's going to be a diastereomer unless you change all of them. And that's the lesson here. So that makes this question pretty accessible. We have a stereocenter here. If we were to do hydride reduction, LiAlH4, and in the second step we add some water to furnish the proton of our new alcohol, the products are going to look like this. We have our established stereocenter here, and actually we have two possibilities. We have this possibility, or with the H coming out, and those would be enantiomers in and of themselves, and we create a new chiral center here. One of them is going to have the new alcohol coming out, and the other will have the new alcohol going in. We can draw our H2 like that. These molecules are diastereoisomers of one another. There's our established stereocenter. It stays the same, whether it's RRS. Our new chiral center is going to have a stereochemical designation. And if we were to just go ahead and label this molecule, this is where colored markers come in handy, is because you can segregate and keep the different atoms separated. So let me get out a colored pen here. Let's do red and blue. For example, this carbon right here, that's the lowest priority substituent, so that's going to be 4. The hydrogen's 4. And we have a carbon there that's got 2 carbons. We got a carbon there that's got a carbon and oxygen. This one wins, so that's a 1. This is a 2, and this is a 3. So the stereochemical designation here is S. and here it is S. Now up here, our stereochemical designation, I'm going to use blue. That's 4, this is 1, this is 2, this is 3, 1, 2, 3, this is R. This one is RS, and this one is SR. This is RS, and this one is SS. RS and SS are diastereomeric isomers of one another. Now, if we look at the second case, I'm going to skip B. I'll come back to it. I'm going to go to C, and there's a reason why I'm doing that. Same reaction, LiAlH4 followed by H2O. What we're going to get is a mixture of two products. We have our two enantiomers potentially from the, two enantiomers from the starting material, but we're just going to go ahead and say that both of these are the same before and after the reaction. So those are the same. Now we're going to have, okay, see that? And then we're going to plus H. Okay, so there we go. Now watch this. I'm going to put an OH here and an H, and put an H here, OH there. These two chiral centers stay the same. The new chiral center has two possibilities. Therefore, we have two possibilities, and that they're diastereoisomers of one another. In this case, LiAlH4 followed by H2O, and we get two possibilities. HOH and OH. And those are diastereoisomers of one another. Now this case up here is really interesting because the products here are not chiral. We have one possibility, LiAlH4 followed by H2O. One case where we have the OH coming out and they're cis to one another, plus one where the OH is going to be going back in. They're optical isomers. They are not chiral, but they do have different chemical and physical properties. Therefore, they are diastereoisomers. This is a case of molecules being non-chiral diastereomers of one another. And that's problem 17.27. We'll be back in just a minute with the next problem, which is 17.31. Bye-bye.